Hello everybody. In this video we will be looking at a few cautions about correlation and regression. We will look at residuals and how they help us, and outliers and influential points, lurking variables, correlation, regression using averages, and the restricted range problem. Correlation, regression using averages. Many regression or correlation studies use average data. That is, you gather many samples, and for each sample you compute averages and then calculate regression or correlation based on the averages. So but we have to be careful when using averages, because correlations based on averages are usually quite higher than those made on the raw data. So when averages are used in place of raw data, the spread reduces greatly, and consequently the correlation coefficient R increases. So the R increases when the spread reduces, and recall that correlation is a measure of spread in a linear relationship. So here's an example. So imagine that we are studying the relationship between age and height of boys, and so we pick many. So we pick a sample of, let's say, sample of 5-year-old boys. And for that sample of 5-year-old boys, we take the average height, and it turns out to be, let's say about 43 inches. And then we do the same thing for at each age level. And so if we use the average height, then it turns out that we get a very strong linear relationship that we have here. Now, so in the first figure, the variation among boys per age class is not shown. That is, obviously not every 5-year-old has height 43 inches, right? So there is a variation in height among the 5-year-old boys. So in the second figure, we still have the same straight line, but for each age level, we have drawn a histogram that represents the distribution of height of that age level. That is, the histogram above 5 here represents the distribution of height of 5-year-old boys. So what we see here is that the mean height represents a distribution of boys of a particular age. If raw data values were used in the correlation instead of the mean, then there would be a lot of spread in the y direction, and thus the correlation would be smaller. So if a parent finds out that their boy's height is below the regression line here, should they be worried? And well, the answer is no. So here I have the growth charts that you typically see from pediatricians. So the straight line here is still the regression line using mean height or average height. And so now we look at these the curves that we have here. So there are boys with above average height, and there are boys with below average height. And the curve right here, this is the 5th percentile curve, and then we also drew the 50th percentile curve and the 95th percentile curve here. Obviously, we can draw many curves here. We can draw the 10th percentile, 70th percentile, 80th percentile, and so on. But we have chosen to draw only 6 of them, 3 above average height and 3 below average height. So it turns out that as long as a boy's height follows a growth curve here, he should be healthy. Obviously, we don't expect all kids to be all kids to grow up to 7 feet tall. So okay, so that's one thing about using averages in place of raw data to do regression or to calculate correlation. The residuals, remember, these are the distances from the data point to the regression line, and the residuals, they reveal the contribution of individual data points to the overall pattern of the scatter plot. Okay, so remember that points above the regression line will have a positive residual. Points below the line have a negative residual. A residual plot is a plot of the residuals. So along the horizontal axis, we still have the number of beers, or the explanatory variable is still plotted on the horizontal axis. On the vertical axis, we are plotting the residuals. So this is a plot of the residuals, and so if we see a random scatter of residuals around 0, which around the horizontal axis here, then we may use that as an indication that a data set fits a linear model, and it is normally distributed and don't have outliers. So again, if the residuals are randomly scattered around 0, meaning around the horizontal axis, then that's an indication that a data set may fit a linear model. So here in the first figure, the residuals are randomly scattered. It indicates a linear trend. In the second figure, looks like we have a curved pattern. So the relationship these are not scatter plots. These are residual plots. So in the second figure tells us that the relationship may not be linear, and the last figure shows that even though the relationship may be linear, the variability changes across the plot. So we see that the variability is changing across the plot. So we need to find out why that's the case. When you make a prediction in areas having larger variability, it may not turn out as good. Recall that an outlier is an observation that is outside the overall pattern. An influential observation is one such that if you remove that observation, it changes the regression significantly. This is often an outlier on the x-axis. And outliers, we know, greatly influence the results. So here's an example. So here we are looking at the age and the adaptive scores here on the vertical axis. So if we look at this regression line, notice that the data point right here, we can think of that is a suspected outlier in this scatter plot. And if we look at this data point, even though it's closer to the regression line, but it is the x value of this data point is kind of quite a bit away from the other ones. So this is a suspected influential point. And then if we suspect so, we can check them. So this would be the outlier in the y direction, and this is the outlier in the x direction. And so here we have these regression lines in 3 scenarios. So the solid red line is the one we get using all the data. The dotted line here is obtained without the child 18, and the black line is obtained. The black one is without. Okay, so the black line is without child 19, and the dotted line is without child 18. So notice that the regression changes significantly depending on whether we include the outliers or not. So we always should observe the scatter plot before running a regression or a correlation analysis. Running a linear regression on a non-linear association is meaningless and misleading. Okay, so here I have 4 data sets, and so I have data sets A, B, C, and D. And the correlations for all the data sets here are all about 0.816, and the regression lines are all approximately the same and given by this equation y hat equal to 3 plus 0.5x. For all 4 sets, you would predict that y hat is 8 when x is 10. So when you plug in x is 10, you get 8. Y hat equal to 8. So again, so what we are saying is that the correlation and the regression lines are the correlations and the regression lines are the same for all the data sets. Now let's look at the scatter plots. So here are the scatter plots for the data sets A, B, C, and D. Now in the first scatter plot, we see, okay, there is moderate linear trend, so regression is okay. In the second one, we see a non-linear association, so regression is not appropriate here. And then in the third one, regression is okay, but we see that there is a suspected outlier, and so we should examine that outlier before proceeding. In the last one, we see that there is a suspected influential point here, just one very influential point. Notice that all other points have the same x value. So in this case, a redesign might be needed, or maybe regression is not useful in this case. All right. So again, the main idea here is that scatter plots are important before running a regression analysis. All right, so now the idea of lurking variables and confounding variables. A lurking variable is a variable that is not among the explanatory or response variables in a study, and yet may influence the interpretation of relationships among those variables. So let me give you an example. Let's say we were looking at the relationship between the electricity bill and the gas bill for my home, and so we look at the monthly electric bills and gas bills, and we plot them in a scatter plot, and we see, let's say we found out that there is a negative linear relationship. So we start the data, let's say from January to December, and there is a negative linear relationship. And so that means that so let's say we are drawing, we are plotting electricity bill along the x-axis and the gas bill along the y-axis, and we see a negative linear relationship. So which kind of makes sense that, okay, electricity bills goes down as we go from January to December, but so this may seem like well and good, but if you think about it, there is a variable which is the time of the year. That is a variable that influences the result here. That is, we know that in the summer the electricity bills are high because we use the AC, and in the winter we maybe the home only uses gas for heating. So in the winter the gas bills are higher. In the summer the electricity bills are higher. So the time of the year is a lurking variable in this case. Two variables are confounded when their effects on a response variable cannot be distinguished from each other. The confounded variables may be either explanatory variables or lurking variables. Association is not causation. That is, even if an association is very strong, this is not by itself good evidence that a change in X will cause a change in Y. All right, so here is an example. So here we're looking at the number of beers versus blood alcohol level. We see quite a bit of variation in back for the same number of beers. So a person's weight is a factor in this study that we didn't consider. So using number of beers as a percent of weight as a percent of weight of a person reduces the scatter. So weight influences the blood alcohol content, and so here weight is a lurking variable that wasn't considered in the first figure. Extrapolation means extrapolation means predicting values from the regression line. So extrapolation or prediction outside the range of the data often leads to incorrect predictions. So what do I mean by that? So here in the first figure, we'll see the regression line. So if we are using the regression line to predict the blood alcohol level for, let's say, 50 beaters, well, then that may not produce a reasonable prediction, because 50 is quite a bit away from the range of values that was used in the study. Okay, so this is it on this section 2.4. I will see you in the next video.